If a kid wants to play soccer, do you first of all, go and read a book with all the rules of soccer and all the techniques, and then go back and I'll let you kick a ball? No. What do? You give the kid a ball and you say, kick it in whatever way you want and enjoy it. Then get a friend and start kicking the ball with them. You learn by playing. And that's how I think you should learn machine learning or anything. I think a lot, people think we're gonna get replaced. And I think we better look for what's not replaceable in us. I think if you try to make the computer do 100% of your job, you'll see what's the 1% where you make the impact.
Yeah.
So where does quantum computing fit into all of these things?
Quantum computer, you have the concept of the qubit. Classical computing, you have the bit, which is a 1 or a 0. It's like an on-off switch. And when you have the qubit, it can be on and off at the same time. This is a bad explanation of entanglement. Imagine that we have two gloves, right and left, and you pick one and I pick the other one, but we don't know which one we picked. And then I go really far to another galaxy, and then you look at your glove and it's the right hand, so you know I have the left hand, right? In reality, what happens is that, let's say you have two qubits and they're entangled, and I take one really far, and when you observe yours, then mine changes. And when I observe mine after you observe yours, you know? But it's not like the gloves. It's not like your qubit knew what was happening and mine knew what was happening. It's that there was an exchange of information happening, which is weird because information cannot travel faster than the speed of light. This is what drove Einstein crazy. The fact is, both entanglement and quantum superposition are very, very, very weird. And you're left thinking that it just has to be a little bit of magic. And quantum computers basically using all that stuff to do better. And this random thing, I can't tell you that it's not entangled with human consciousness or with God, whatever, you know what I mean? Like, if it's a completely random process that doesn't depend on the inputs, there's nothing of me that says that thing didn't entangle with my consciousness.
Our guest today is Luis Serrano. He's the founder and chief education officer of Serrano Academy, a popular YouTube channel that makes machine learning and data science concepts simple. He previously spent time at Cohere, was a lead educator at Udacity and Apple, and worked as a machine learning engineer at Google. In this episode, we cover why most people underestimate their abilities and how to tap into hidden skills. Luis shares game-changing strategies that make even complex topics feel natural. When AI knows more than humans, what happens next? What is quantum computing? Why it matters? And why it might change everything. If you've ever doubted yourself, struggled with learning technical topics, or wondered what your role will be in an AI-powered future, this conversation will change the way you see yourself and the world. Don't miss it. If you enjoy this content, subscribe to Data Neighbor in your favorite podcast app and YouTube. Let's dive into our conversation with Luis Serrano.
Hey everybody, welcome back to another episode of the Data Neighbor podcast with Shravya, Hai, and Sean. Today our guest is Luis Serrano from Serrano Academy. Welcome, Luis.
Hi, thank you for the invitation. I'm happy to be here with you today.
Hey, Luis, welcome.
Hi, Sarya. How's it going?
Thank you for taking our podcast to the new heights.
Thank you. Thank you for the invitation.
Yeah, exactly. So, Luis, you are pretty famous for being a well-known educator in the online space. For those who are not aware, definitely check out Serrano Academy on YouTube. So let's jump right in. On your YouTube channel, you make these really beautifully explained videos about core concepts in machine learning, data science, and topics like that. I have a two-part question for you. What got you interested in doing that? And then I want to get into an anecdote of your life that actually was pretty interesting, I thought.
Okay, great. Yeah, I've always been an explainer, even if I don't know about it. Originally, I'm just a really bad understander. Like, I have a hard time in school. I was very slow. And I just don't understand things, the abstraction of things is difficult for me. And so that, even when I was in grad school, when I was a mathematician or when I was a programmer or data scientist, like I've always been slow at thinking, and I have a hard time thinking in high level. But I'm always the one that explains the stuff because I always have to tell stories in my head for me to understand stuff. And so I kind of gravitate to that. And at some point, I changed careers a couple of times. And at some point, I just decided, you know what? I think the one thing I do best is explaining. So I'm just going to start doing that. And out of that, the YouTube channel started, but a few other projects started, the book and other courses I taught at companies. But I would always gravitate towards explaining stuff. And these stories that I tell are the stories that I tell myself in my head, because I need to explain things to me first to be able to understand them. Other people that I know, colleagues, they can handle abstraction and work with it, but I can't. I have to tell a story. So when I share that story, I already told it to myself, so it's kind of, that part is for free.
Also,
Got it.
another
Yeah.
thing, Luis, before we go into the second part of the question, you did work in the industry, right? You had industry experience
Yeah.
and then you moved on into the education. So you were at Google and Udacity.
Yeah, so I was in academia many years. I was a mathematician, so I was in a researcher at the university and taught and stuff like that. But then I moved to Google. I got interested in machine learning, so I was at Google for a while, and I was a programmer. But I'm so as a programmer. I'm not that good, and I don't enjoy it that much. But I was always sort of I would be put for like giving the talks or anything that was educational. When I was like a visitor, like I would go give the talk. And eventually I decided that maybe that's what I should do, because some stuff was very difficult for me and the teaching just came out easy. And so I switched to Udacity, which is the best decision I've taken in my life, because I came in as a machine learning instructor. This is like 2016, when like sort of the boom of AI, when it started like analyzing images and realizing that a cat's in an image and it looked amazing, and a lot of people were interested in learning. So there was a big boom in machine learning education, and so I came into Udacity to teach their machine learning courses. And there was a team that was wonderful, and I was sort of put to lead that team, and we just built so much material, and I learned so much stuff when I was there. And then I kind of kept teaching. Like I was at Apple, and I was teaching at something called Apple University. Like I've been at different companies, but I'm always the explainer in the company.
That's amazing. I mean, like, in order to teach something, you have to deeply understand it yourself. So I guess my second part of the question that I thought was pretty interesting, which is you were a mathematician, but then
Yeah.
at an early age, I think you told us that you thought you couldn't learn math. You kind of touched upon it a little bit. How did you go from that to now teaching very complicated mathematics and statistics to people?
Yeah, this is a funny story that happened when I was like in grade 8. I was failing math because I found it really difficult. Like the formulas made no sense. And so I was just one more person who says I'm bad at math. And so I was failing it really poorly. But I took an exam. This was in Colombia, where I grew up, and I took an exam for the math Olympiads, which I only did it to skip class, because if you go sign up, you skip 2 hours of class and then you just doodle for 2 hours. But I enjoyed this exam because it was like puzzles, and I like puzzles. I always like puzzles and little games and stuff like that. I just never thought it was math. And so I did this exam, and then I thought it was fun. And then the results came out, and so the teacher came to say hi to me, and I didn't think he knew me because I was the worst student. But then he was congratulating me. He's like, "You did well. You were first." And I was like, "Oh my God, I've never been first in school." And then he said, "No, you're first in the country." And I was like, "Oh." And then
My God.
yeah. And then I found out that I actually was good at math, like many people who are good at math and never know, because math was taught to me like formulas. And so I started going to these trainings. The price doesn't look like a price, but the price that you get to go to math camp in the summer. But I loved it because they would do it completely differently. They would give you a problem, and then you figure out how to solve it. They wouldn't teach you how to solve it. You just start finding techniques, and then they give you some techniques, and it was kind of like, it was exactly the puzzles that I always liked, not the formulas that they give me. Because in school they give you a formula, and then they ask you stuff about it, because they turn you into an instruction follower, right? Like an obedient instruction follower, and they never sort of give you much room to explore. Whereas in the Olympiads, you could explore the whole thing. So math became fascinating to me, and I was still not doing well in all my other courses, and so it just made sense that I would study math when I graduated, because I was like, well, anything else, I'm not gonna do very well, right? And this was like in the late 90s, so everybody was telling me, no, you're gonna starve if you study math, because data science didn't exist, right? But I was like, I'll starve if I study anything else. So I did it, and then I realized what happens when you, like the academic career, which I didn't know what it was, but it's like you then do a grad school, so I did a PhD, and then you do a postdoc, and then you become a professor. And every time I wasn't really thinking of the future, I just wanted to do more math for a few years. So I would take the step that gets me to do math for longer. And then eventually I switched later in life. I really enjoyed all those years of math.
Nice, very cool. And
Yeah.
you kind of attributed that to the fact that different people learn things differently, right? Like it's
Yeah,
not
yeah.
purely because math is not easy to you, but just you learn it differently. So I think
Yeah,
especially in today's world, right? Like for example, like AI, machine learning, all these concepts, there's a natural barrier that it carries the
yeah,
connotation that hey, it's really, really hard. And so many
yeah,
people either look at the surface level of it and be like, hey, I'm done, like that's too hard. Or
yeah.
some people try a little bit, but then still can't do it because that's the textbook based formulas and stuff to begin
Yeah.
with. What's your advice for them? Like to not miss out on just learning, be curious.
Yeah, things don't have to look so complicated, and educators, many of them, not all of them, but it's a trend that they teach you stuff in the most complicated possible way, and you can always make things complicated, right? Like if I explain to you how to boil an egg and I explain it in Hungarian, let's say you don't speak Hungarian, if I just play, then it's gonna look really hard. But it's not that the boiling egg is hard, is that my explanation was awful, right? And I need to just say it in a language that you speak. And the same thing happens with math or machine learning or anything in STEM, but actually most things are poorly taught because they're taught to us in a language that we don't speak, which is the language of abstraction. The language of abstraction is a language. There's a few people, and they're the academics. They're the ones that are that who handle abstraction better than handle the concrete stuff. But the other 99 point something of us are better at concrete stuff, and we are used to things that are like in the real world. And if they explain something to us in the real world, we're used to it. So people know so much more math. People know so much logic, so much physics. Like if I say to somebody, draw the equation, I don't know, y equals minus 9.8x over 2x squared, they don't know what to draw. But if I say, draw a tennis ball falling from a building, everybody draws a parabola. You know what I mean? So like everybody knows, we live in the world, we know physics, otherwise we'd be falling all the time. And if we didn't know logic, we would be breaking all the rules. So we know a lot more than we think. And many times, yeah, when you take a concept that looks complicated because it's taught in a weird language, and you turn it into a real life scenario, and you make it a problem that is in a real life scenario, people solve it, but they can't solve it in abstraction. So I try to do that, and I try to encourage just people to do that and empower people, because when people realize that they know a lot and that they were able to solve a problem that otherwise looked hard, they feel empowered, and they become braver, right? Because we need to just feel like we can handle concepts that are complicated instead of making people insecure.
I think that's the key, right, Luis? I remember this from our conversation when we're just getting introduced.
Yeah.
Is people know a lot more than what they think they know.
Yeah.
I think that's the message that's like so strong and so empowering when so many people out there who are trying to get into interviews, who are trying to study and, get through their courses, and like people who are trying machine learning or AI now for a new thing, and they are like, oh, this is not for me. They don't even know that they know a lot more than they think that they know. And It's all about learning it in a way that they could resonate with and relate with. That will help them probably get into that path of learning way faster, and make them aware that they actually are good at it.
Exactly, yeah. And the complexities can come later, right? Like I think there may be some complexities, but they shouldn't be the first thing you see. And I always made the comparison with music, for example. Like music is complex. Like theory of music is as complex as mathematics, right? Or physics. But nobody says, oh, I'm so bad at music. Nobody says that. Right? But everybody says I'm so bad at math, but it's just as complex. And the reason is because when we get introduced to music, we get introduced in a friendly way. We start like as babies, we hear lullabies and we sing songs and a happy birthday song. And by the time we realize that there's a lot of scales and stuff, we're not afraid of the subject, right? Whereas in math, the first thing they do is they write a formula on a 2x4 and smack you in the head with it. You know what I mean? Like they just and so people don't like it. But if we did it the opposite way around and we start telling people the fun part of it, making them solve fun puzzles or word problems or things like that, and they like it, and by the time they get to they see the formulas, they know that that's not it, and they're not scared anymore, right?
Yeah. I mean, I think we were talking about kids and how kids are taught division, right? Like,
yes,
divide this, I don't know, like, or in like a number of birds that flew away from this wire that they were sitting on, and something that they can't imagine, like a 5-year-old, 6-year-old. But if you teach them about chocolates, like there are 6
Exactly.
chocolates, and you and your sister, what do you want to? How many do you get? They're like 3
Exactly.
for me and 3 for my sister. I'm bigger, so I get 4. She gets 2. So
there you go.
that
Weighted
logic
averages.
right there.
Yeah.
Weighted
There you go.
average right there.
And
Exactly.
yeah, I love that example. Like, for example, you know how many people think that a quarter is bigger than a third? You know, that's what, like, for example, in the US, somebody, I don't know what company, what chain introduced the third pounder, and it didn't do as well as a quarter pounder from Burger King because people thought a quarter was bigger than a third, right? Like, so people think
1/4 and 1/3.
people think things like that. But if you tell a kid, okay, I got these candies, do you want to split them with 2 of your friends or with 3 of your friends? What would they prefer? Then they know that a third is definitely bigger than a quarter because you made it easy, right? Like, but if you put a third and a quarter, like it's not so obvious, right? So yeah, with candy is the best way to explain math.
Basically, speak to the language that they're already used to in their heads.
Of course.
Without logic, people wouldn't live their lives. Like everyone's doing math right now for even the most uneducated. Probably as soon as you start walking as a human, you're calculating. You're calculating where you're going. You'll hit yourself. You're calculating when there's a small piece and a big piece of a cookie. Yeah, I want the big one. There's, larger, smaller, like all of this is happening in your head. So talk in terms of how they are living their life so that it gets, the concepts get more easier.
Exactly. That's what you gotta do.
Yeah. I mean, I really appreciate educators like you, like Josh Starmer, like
Starmer, yeah, he's awesome.
Martin Grutendorst.
Who
we all had on
our Martin Grutendorst, the book. Yeah,
like
the Alamar is co-author.
We gotta get him on a pod.
You should have him,
I mean, like, honestly, if I were in school and I had access to content like this versus the textbook I was banging my head against, I feel like I could have gotten a PhD. Maybe not. But
definitely,
for me, I thought I capped out at what was the easiest math in college? Like whatever that class was. I thought
algebra, calculus.
Yes, I think. That's where people start.
They make it hard. They make it hard, I always make my material thinking of that, thinking like, what would I have wanted? How would I have wanted to learn it that one time that I was so confused, right? And I still, to this day, I still learn for the first time things that I should have learned and that I saw, that I remember the name of it, and never fully understood it, but the name stuck with me, and I learned it late in life, because I try to, my first audience, I try to teach myself many years ago.
So Luis, just to take this further to our audience, and we have people from data and ML and data science, right? So can we take one concept that we see people generally falter, or like this is too complex, especially when they're trying to learn, and teach from your perspective, maybe a couple minutes? Do you want to do gradient descent?
Yeah, sure. Gradient descent is good. Yeah, actually, that's a good one. For example, let's say you wanna, the way they explain it in the complex way is saying, okay, you have a function and you want to find the minimum of this function. So what you do is you take the gradient vector upside down triangle, that's a nabla or some letter. And then you take the negative of that, and then you take a step of epsilon in that direction, and then you iterate. Like, that's awful, right? But then if you say, okay, if you're standing in a mountain, somewhere, and you're kind of lost, and you can't see too far because it's foggy, and you need to get to the bottom of the mountain, and you cannot see, it's foggy, so you can only see 1 meter around you. How do you get down of the mountain, or at least how do you approach the problem, right? Well, one thing you can do is you look around and you see, well, if the terrain is uneven, if I take one step, what is the direction where I lower the most, where I descend the most? And you take a step in that direction, and then you're back to where you started. You say, okay, now I look around me and say, where can I take one step? You would always walk in the direction that descends the most. And maybe that takes you to a valley, and doesn't take you to the bottom, but it's the best you can do, right? Like you can't go up. And so that's gradient descent. You look around you, you see what's the direction that you descend the most, and then you descend. And now why is gradient descent used? Well, because you want to, in a machine learning model, you want to do the best possible, right? Like in an exam, right? Like you want to do as well as possible. And there's something that measures how poorly you're doing, which is called the loss function. And it normally looks like an ugly formula, but it tells you how well you're doing. If it's a big number, it means you're not doing well. It's like you have a lot of mistakes. And if it's a small number, then you're doing well. And you want to decrease that number of mistakes as much as possible. And if the number of mistakes is the height that you are, then you want to basically get down from that mountain. So when you train an ML algorithm, you're measuring how bad it is, and however bad it is, you try to reduce it by descending from that mountain. So that's kind of gradient descent. That's kind of how I look at it.
That's so cool.
So
I don't know. What do you think?
Okay, that's so
No,
cool.
it's pretty cool. It's pretty cool. It's like you're stuck on a mountain. You're stuck on a track. You have to get back. What do you do with whatever you have in front of you? Right?
There you go. Yeah. So there's
Yeah.
two reasons the logo of my channel is a mountain. One of them is that gradient descent is one of the first explanations that I have, and I said you have to descend from Mount Everest, like Everest, but Everest because it's the error.
Oh, that's
And
so
then
clever.
Yeah, it worked out, and then I realized that mountains are really prone for that. Because then I got tired of using Mount Everest, so I started using Mount Kilimanjaro. And then I started making up errors with all the mountains, and it turns out they all work out. When I really realized I hit a spot that I should stop is when I started looking at the Icelandic volcano that stopped a lot of flights back in 2012. Remember that it exploded and a lot of flights in. And it was called, I may get this wrong, so there's an Icelandic person in the audience, I apologize, but it was called, I think it's like Eyjafjallajökull or something like that. But then the Icelandic word for error is vidla, so I just call it the Eyjafjallajökull. But then when I got there, I realized, okay, I need to change the joke. I'm getting too far. That's one of the reasons why my channel has a mountain, and the other one is because my last name means guy who lives on the mountain. You know, Serrano means guy who lives on the mountains, because the Sierra is the mountain, right? Like Sierra Nevada or Sierra Leona. So I put a mountain for that reason. That two reasons.
So if people didn't understand why I said Luis made our channel go to new heights, it's because of that too.
Because we're going up a mountain. There you go.
And also because of Luis, yes.
I also grew up in the mountains in Colombia. This is the Andes, like 3,000 meters or something. Yeah.
Oh, that must be an amazing
a lot of mountains.
experience.
We got to name this episode something to do with mountain.
It gotta be with mountains.
Yeah, we're gonna get a little.
Definitely.
That's so cool.
Yeah.
Hey, Luis. So for people who have a fear of complexity, for example, and they're like, "Hey, is machine learning for me?" How do you advise them kind of get started in that space to break through that barrier?
That is a great question. I have a way to learn, and it's basically I see a lot of experts that say the opposite. So I wanna the way of learning is basically a lot of the experts tell you, okay, you gotta go and learn all the math, because if you don't know math, you don't know machine learning. So go learn all the math and then come back. And then you gotta learn how to program. So go learn all the programming and then come back. And then you pick up your first machine learning book and start reading the machine learning book. I don't like that. It'd be the opposite, right? So I think if you're gonna start, for example, if a kid wants to play soccer, right? Do you first of all, go and read a book with all the rules of soccer and all the techniques, and then go back and I'll let you kick a ball? No. What do? You give the kid a ball and you say, kick it in whatever way you want and enjoy it, right? Like learn to enjoy it, learn to get better. First of all, see if you enjoy kicking the ball. If you don't like kicking the ball, soccer's not for you, right?
You shouldn't be, yes.
Yeah, you're in the wrong. So just kick the ball and then do that enough, and then get a friend and start kicking the ball with them. And then if, after a while, I'll come back and I'll be like, okay, now let me teach you some rules. You have to kick it like this. This is a technique. This is how it's scored. But you learn by playing. And that's how I think you should learn machine learning, or anything really. And so when people come to me with machine learning and they go, oh, how do I learn the math? I'm like, don't worry about the math. It's not don't worry about the math as in like you don't need to know math. Because sometimes people misunderstand me. Like, no, but start playing with it. Like, take a data set that you like. I don't know, a soccer data set, tennis data set, cooking data set, anything you like, any hobby you have, and start analyzing it. Plot it. Okay, then you find out how to plot it. in SQL or in Python. You don't have to learn how to use the whole language. Just learn the line that gets you to plot it. And then start playing with it and understanding it. And then maybe you see a line forming somewhere. So, okay, maybe that's because you got to learn linear regression. Go learn it because you now have a frame of reference on how to learn it, right? So start kicking the ball. And that's how I tell people to learn it, and that's how I learn stuff myself. Even new stuff, I always like learning new stuff. I've been like learning to play the piano recently, and I decided I'm gonna do it my way, whether it works or not. And I decided I'm just gonna learn songs, and I don't know what's going on, but I'm just gonna learn a song, and then I learn another song, and then I learn another, and then I say, oh, okay, you know what? This chord's actually keep getting played a lot, so then I go find out what it is. Oh, it's a major chord, like that, right? So that's how I like learning stuff, and that's how I tell people to learn stuff.
So learn by application. You basically understand the where is the concept used, so that when you learn it, oh, this is why this is like this, rather than you learn about linear regression, understand how do you do R squared, what is this different types of errors, and you just by heart them without knowing what it means. Versus now that probably a height and weight chart or something like that.
There you go.
Like a really simple data that you can get anywhere and plot a line and see this is something that could correlate.
That's a great example.
This is something I could just use simple linear regression to solve me an equation that fits the line.
I love that example, because if people may not know linear regression, but anybody knows that if you're taller, you're probably heavier, right? Not necessarily, but there's a kind of correlation, right? And so that's linear regression. If you're taller, you're probably heavier, right? And if you were to plot height and weight, then it kind of must look like a line with a lot of, it's a wide line because there's a lot of variance, a lot of error. I love that. I love that example. Yeah. And associate it with fun. I think if you associate it with something fun that you're doing, then the learning happens more organic. Like when I started learning machine learning, which is way into adulthood, I just picked a tennis data set because I like tennis. And so I started plotting stuff and making little models for things. And that was fun. And it didn't feel like I was learning. But if I had learned linear regression many years before in university and never made sense to me why you would want to fit a line through stuff that's not linear, right? That's not natural. But then you realize, it's to make predictions. It's to understand your data. So,
absolutely. So what is machine learning? Machine learning is something like we talked about math, right? We do math as a kid. And machine learning is something that we all do in our brains, and we are trying to automate that on computers. So when you see two players playing in tennis and you see one doing a better job, they have more energy, they are hitting better, they are making less errors, there's a high chance of that person winning the race. And that's a machine learning model right there. If you have a time series plot and the sets and every detail of how they're moving, maybe if you have a really detailed data set, right? Then the training could be around, did they win or not? Yes or no?
Yeah.
And, and imagine if you yourself know that you're a subject matter expert or you follow tennis, you know the details. It's literally replicating what happens in your head on that, on whatever Python or whatever you choose to be. And it makes things so much more easier because you come with a hypothesis. I might probably see this, and see this when I see number of, strides made or the number of movement on the court, how fast they're moving, if you have a speed. I don't know if all of this is correct in the data.
Makes sense.
That's what I could think, right? And that makes it so much more easier for you to stick through the entire learning. Because if you choose something probably, I don't know, going into space and you don't care about rockets as much, then you would hate that.
Exactly.
Model versus something.
Exactly. I love it. That's a great explanation. Yeah.
That's awesome. Hey, I think that's a good segue into this other topic that I think you have a lot of thoughts in now that we get into machine learning a little bit. So with the advent of machine learning, AI, all these stuff that makes our lives easier, makes people more productive, and everyone's getting into the field. What do you see? You have a lot of thoughts around what that means for the future of society, right? I'm just going to zoom super high level here.
Yeah.
And we're going to review why we're talking about this, because for our audience, it's going to be really cool. So can you describe a little bit about your thoughts around this?
Yeah, great question. Yeah, I think about this a lot. Because we're at a an interesting point of society, right? Like where like computers are doing a lot of stuff and people are scared, right? People are thinking, are we gonna get replaced? What's happening? And I give that a lot of thought, and I look at the past because a lot of times things behave the same way and we have to adapt, right? And I look at, for example, like at some point physical things were our best bet to survive, right? Like if you run faster or you are stronger, then you're more likely to survive, or you're more likely to succeed, right? Because you would hunt that buffalo or run away or that kind of stuff. But machines started doing that for us. And now that's not so important. We still do it, but machines do a lot of our physical stuff. So then we went to the rational part. We went to the brain. And for many years, the brain was the king and the main thing. But now we're starting to see that machines are doing that for us. And in the same way that I can't run faster than a car, and that Usain Bolt can run faster than a regular car, I feel like humans don't have much of a chance with computers. We already lose at chess for like more than 20 years, and we lose at Go. And pretty soon we're going to lose at math and physics because these machines just replicate our rational process and do it better. I think a lot, people think we're going to get replaced. And I think we better look for what's not replaceable in us, right? And so I have a pyramid in my head. The first level is physical stuff, the physical strength. The next one is rational thinking. And what's up there? What's next? And I think there's a few things that machines cannot do, and they're going to be what we can do, right? And one of them is things like empathy, right? Things like emotional intelligence. I don't think machines can do that. Machines can calculate stuff, maximize a number. But a lot of the decisions we take are not taken like that. A lot of the decisions we take are based on emotions, not so much based on rationality. And a machine can't take those. So I think this is something that we may have overlooked as a society. Some other societies have overlooked it less than Western society. We've overlooked that. We can call them soft skills. They're not. They're the hard ones. They're the difficult ones because a machine can't do them, and we need to go there. And I even go one more level. I have one more level in this imaginary pyramid I have, which is up aside from emotional. We have rational intelligence and then emotional intelligence. And I like to think of intuitive intelligence. This is something that we have very not developed, which is when you just get an idea and you don't know where, like your gut feeling, right? Like, and that's not, ChatGPT can't do that. I think we have another place where that idea comes from. And we don't listen to it so much because we put too much rational thought into things, which is not bad to think rationally, but sometimes you need to not think to be able to make a decision, right? Sometimes you need to clear your head and the decision comes in. Many times you take a decision already and then you try the numbers to work. You try to work out the numbers and then we pretend that we took a rational decision, but we made the decision before. So that's something we need to cultivate, and other cultures have developed it way more. Buddhism has developed it way more. Like in the Western society, we shut down that voice. I think if we want to do it well, we need to start doing that. And then it's scary, right? Because when I think of future humans, we always think like really smart humans, right? Like really smart, like the kids are going to do quantum physics at age 5 and stuff like that. I don't think that humans in the future are going to be that smart. We're going to have less skills like writing an essay. They're not going to be able to maybe so easily, and they may not do math so well, but they're going to have other skills developed that we don't have, that are going to be the important ones. In the same way that if you look at my great-great-great-great-great-grandpa, they're going to be embarrassed to see my arms, right? Like, because I'm not as strong. They're going to be embarrassed to know that I don't know how to make fire with 2 rocks or hunt a buffalo or a mammoth or something. You know what I mean? Yeah. But I have skills that they don't have, which at that time may have been useless, but now they're very useful. So my great-great or great-great-great-grandkids may sound stupid to us. I think they're going to sound stupid to us. But like we look weak for the Neanderthals, but they're going to have a whole set of skills that we perhaps can't even imagine. And I think AI is sort of helping push in that direction, because it's starting to do things. Like if we say something that a computer does, like once the cat's out of the bag, that's not a skill of mine. And it sounds harsh, but it's like the moment you remove those skills and you focus on other stuff, I think that's the way to sort of grow as a species. I don't know.
That's just so futuristic, this conversation.
Luis, if you were to put bets, what are the evergreen skills that people should pay attention to?
Yeah, I think either evergreen or for some time green. Definitely emotional intelligence.
Long-term green.
Yeah, emotional intelligence. I mean, I think people are starting to catch on to that. Like previous generations put 0 effort there. I think our generation is putting effort there. Anything regarding empathy, anything regarding that. And I think, yeah, I think listening to your inner voice, I think intuition, meditation is definitely very important. Those kind of things are getting more and more important because our rational intelligence is being replicated. Like the smart kids are getting, like, we're going to get beaten by a computer. So I think we need to develop those things.
Oh, interesting.
I feel like I don't know, this is just do you think more like physical realm related things like entertainment, like probably that video also can get, replaced with AI, video and music and art is also getting replaced. Probably food is something that will not get replaced with
Yeah.
AI.
It's hard, right? Yeah, it's hard because I wouldn't want, I don't know, I think there's a special part of art that's us, and there's a part that is mechanical. Like maybe thinking of the painting you're gonna make is much more high level than actually like figuring out the colors. And I'm speaking out of ignorance. I'm not an artist. But I feel like a lot of things are counterintuitive and may look sad, like that we're gonna skills that we're gonna lose. But I think there's a 1% on every skill that is unreplicatable by a machine, and we're gonna end up doing that. Which is like walking, for example. Like we don't walk that far anymore, right? If I need to go farther, I use a car that does 99% of the physical work or more. I just do a little bit of like shifting, and pedals and stuff like that. But the physical stuff I do is much less than what the car does. But I still tell the car where to go. And when there's autonomous cars, I'm not gonna do any work, but I still tell the car where to go. So like, there's that 1% of the human input, which I think and I hope in art may be like that. Maybe there's a 1% of like the inspiration of the artist that is not for a computer. A computer may always just replicate older stuff. And there's that 1%, and then machines will help us get farther, right? Like we also do that, right? Like AutoCAD, like architects use for a while a lot of software, but they still have sort of their creativity. And for example, yeah, like educators, right? Like I feel like I may be replicated with like videos and stuff, but I think there may be an iota of ideas that we put. And I think the best way to do is try to get replicated as much as you can. Try to get the computer to do everything, and you're gonna see where it falls short.
That's
and
amazing.
Then where that falls short, that's you. So I use language models to make my videos now. Like I just start asking it stuff and making it explain stuff to me. And if I let it alone, like it doesn't get that far. There's a little bit of the way you push it that is still you. That may get replicated soon, and then I won't know what to do. But I think if you try to make the computer do 100% of your job, you'll see what's the 1% where you make the impact.
Yeah, I love that. Luis, this is what I even tell like my cousins and friends and even my parents who are not in tech, is to start using chat to just understand what can it do for you, right?
Yep.
And what you're telling is that balance is what you are, who you are, and what you bring to the table, what you bring to this world, and hold on to that and try to increase more of that, right? Try to get more of that, and that's what you bring. Yeah,
Absolutely.
pretty cool.
Yeah, I agree.
What have you seen, Louis, in your time, probably with videos and LLMs, or maybe your actual education or with ML models? Like, where do you see that you still have to bring in, like your input, that you see that LLMs are still not doing a good job, that you foresee them continue to not do a good job in that area?
Well, yeah, that's a good question. I feel like asking, and this is coming from when I was a researcher, I feel like asking a question is harder than answering the question, A good researcher asks the right questions. And so I think and that's prompting, right? And so when I try to learn something new, before I used to read stuff or find it in Wikipedia, watch a lot of videos, bother all my friends until they're sick of me asking them stuff, like any expert friend, like I just go ask them. Now I just start prompting the model. And I find that if you give it a normal question, they will answer it in the most standard way, like the Wikipedia way. And so I just have to basically say, I don't understand this part. Tell me more about this one. I give it the direction. I say, okay, try to do it with this example. This particular part here made no sense. I feel like I just guide it with questions, like a kid that keeps asking questions, right? And why, and why, and why. I feel like if we have that, like that thing that we lose at some point in our life and we should always have, which is asking questions, is what I think is one of the biggest skills that we have and one of the things that make us more human,
I mean, it's so fascinating you said that because don't we always joke about executives always just ask questions? Like executives in the
Yeah,
company, right? Or
yeah,
people giving orders, like they just ask
yeah,
questions, they never
yeah,
do anything, right? And then
exactly.
going back to the kids example, they also ask a whole bunch of questions and they never do
Yeah,
anything. So inherently, we're actually programmed to just ask questions,
yeah,
which is itself is like just a human nature. And at some point, either the education system or whatever makes us become like answerers. But I mean, like,
yeah.
not to get meta about all of these, but like it feels like we're being being either an exec or a kid again, but that they're all two of the same things.
Yeah, I agree. And I think, yeah, I mean, and I love the fact that now we have a machine that we can just ask infinitely many questions, because I've been going crazy. It's been a lot of fun. Yeah,
No, I love
Nice.
the executive example too. Hi. It's almost
yeah,
like you have your own big team to answer questions for you,
there you
Yeah.
go.
right? So no one, not what is stopping you from being an executive of your own company or
Hmm.
in your company if you are like, working on something, what's stopping from you to showing business impact or, showing some value because it's not just you anymore. You have so many other agents of the future,
Hmm.
whatever you might call it, to
Yeah,
help you out on it. And probably that's where they ask for us to have higher productivity, right? Even a
hmm.
team of 20 could be like a team of 100 with maybe 5 agents for each of them to help handle
Hmm.
like, the team. So no more need of managers,
Yeah.
yours. Yeah.
No, that makes sense. And I think it in academia works too, right? Like if you look at the CEO in academia would be like a professor, like a principal investigator or someone who has works with postdocs and students, and they just ask the right questions. They just go, okay, what if we go in this direction? And then the others, they follow that. Like when I was doing my PhD, my advisors just asked questions, be like, hey, what if we blah blah blah? And then I would just go and work in that direction, right?
Yeah.
So I think that that's definitely one of our nicest and more fun and best skills.
That I gotta extract this to the trailer somehow. I feel like this is
Cool.
at least it's a light bulb moment for me. Hey Louise, so where does quantum computing fit into all of these things? I think
Yeah.
like you are really deep into quantum computing and you have also a lot of expertise around that. Can you explain as if we're all have no idea what that is and in this world that you just described, where does it fit in?
Well, yeah, absolutely. The funny thing is that I think we all have no idea what that is because the experts, there's a saying that says, if you think you understand quantum computing is because you don't understand. Sorry, quantum physics is because you don't understand quantum physics. Because it's so bizarre that the more expert someone is, the more lost they are. And when you ask an expert, every time the answer is always like, well, you like they always start because it's so bizarre. It's one of those things that I think, and I know some of it. I mean, I enjoy it, but certainly I'm still sort of feel like I'm still learning new stuff every day. But basically, it's one of those things where the model that you built is the one that best fits what you have, but there's no reason that that's actually the truth, right? It's just you just discard other things. And so basically in quantum computer you have the concept of the qubit, right? You have the concept of the like in classical computing you have the bit, which is a 1 or a 0. It's like an on off switch. And when you have the qubit, it can be on and off at the same time. And it's like a slider that you can put on or off, or like in romantic, like that kind of stuff for the lights on or off. But it's more like a sphere where if you have it on the North Pole, you're on. If you have it on the South Pole, you're off. And if you have it anywhere in between, it's kind of part on, part off. Like if it's in the equator, it's 50-50, right? But here's the bizarre thing. It's if you haven't looked at it, it's not decided, or at the very least, that's what the only explanation that fits, which makes no sense. Because imagine this: if I flip a coin and the coin fell, I don't know what the coin is, but the coin is either heads or tails already, right? Like the universe knows. I just don't know. Maybe someone else saw it and knows. I just don't know, right? And it would be tremendously arrogant of me to say, well, if I don't know, then neither does the universe. No, the universe no. The coin is heads or tails. The only thing that changes when I look at it is that now I know one bit of information, right? One bit literally. Like I know more information, but I just found out. But what happens in quantum computing is if you haven't looked at the qubit, it's both. And the moment you look at it, it decides if it goes up or down, right? And there are experiments that show that no, it's not that the qubit knows. It's not that the universe knows. If the universe knows, then the math goes differently and the experiment goes different. The only thing you have left to think is that it's both at the same time, which is very weird. And then there's also something called entanglement, which is even more weird, because it's like this. Imagine that, let's say this is a bad explanation of entanglement. Imagine that we have two gloves, right and left, and you pick one and I pick the other one, but we don't know which one we picked. And then I go really far to another galaxy, and then you look at your glove and it's the right hand, so you know I have the left hand, right? That's a bad explanation of entanglement, because in reality what happens is that, let's say you have two qubits and they're entangled, and I take one really far, and when you observe yours, then mine changes. And when I observe mine after you observe yours, you know? But it's not like the gloves. It's not like your qubit knew what was happening and mine knew what was happening. It's that there was an exchange of information happening, which is weird, because information cannot travel faster than the speed of light. This is what drove Einstein crazy. So if you looked at your qubit and mine changed immediately, this happened faster than the speed of light, which is, Einstein hated this. He called it spooky action at a distance. Like, anyway, the fact is, both entanglement and quantum superposition are very, very, very weird. And you're only left with, you discard so many hypotheses that would make sense because they don't match the experiments, and you're kind of left thinking that it just has to be a little bit of magic. And quantum computers basically using all that stuff to do better. So when you do a calculation on a qubit, for example, if I have, I'm going to simplify this maybe more than I should, because I'm not sure if I'll get it correct, but basically, yeah, go ahead.
Before we get into it, please remember what you're going to talk about.
Yes.
Right? But what the heck is quantum computing? We hear it about it, right? I know qubit. I understand, like, we talk about qubits. Entanglement I've heard too. But I'd love to understand if, let's say, I'm showing it to, like, my 10-year-old cousin, like, my brother's son, and he doesn't know quantum computing. He just heard its name. What do I tell him if he asks me, hey, what is quantum computing and what does that even mean? What are we going after? What's the problem you're trying to solve? Yeah, you're trying to, the big application is that you're making two things. One is faster computations. And by faster, I mean not just a faster computer, like ridiculously faster. Exponentially,
yeah. Like problems that are, like, it's not like if I take a much, much bigger computer, that's a quantum computer. No. There are problems that no matter how big the computer, complexity, how hard the problem is, grows faster than the size of the computer. Quantum computers would solve that problem, right? Like if I, for example, like the traveling salesman problem, let's say, if I have 10 cities and I want to visit all the cities as fast as possible, that's a hard problem. But let's say I have enough computers to solve it, and I add one more city, the problem gets way harder. And I add one more city, and so I have to get exponentially more and more and more and more computers. So I can't solve it with a classical computer, because you can always make the problem bigger and bigger and bigger until I run out of computers. So that's where a quantum computer comes in. It grows at the same rate as the problem. Like if I have one more city, I just get a bit of a bigger computer, but I don't need to get twice as many computers. You know what I mean? So the key of quantum computing is, well, one of them is that it can sort of, and this is the part where I'm going to kind of lie, but not really. It can sort of do two computations at the same time, right? If I have to, let's say I have a bit, and it could be 0 or 1, and I want to operate on it. I want to add 1 to it, or I want to multiply by something, whatever. Then I have to do two operations, one on the 0 and one on the 1. And okay, that's just 2. But if I were to do it again on both, then it's 4, and then I want to do it again on both, then it's 8, and it just grows exponentially. Whereas if I have a qubit and it's on perfect superposition, let's say it's in a superposition of 1 or 0, and I operate on that qubit, I'm doing one operation, right? So one operation here and 2 on the classical ones. And so when this grows exponentially here, this doesn't grow exponentially on the quantum computer, right?
Because it can be 1 and 0 at the same time?
Yeah, so if I operate on the 1 and the 0 at the same time, then I've done one operation on the qubit, but I operated on the 1 and on the 0, right? Now, here's the problem. You can't see the solution. So, because when you look at it, then it becomes one of the two, and then you never knew.
Yes.
And then you never knew what happened with the other one, or what you even had. So you got to be really clever with the quantum algorithms and play with them and operate with them and twist them around, so that when you get the answer, you can sort of read what was going on. So that's the non-trivial part. But in principle, you can operate on two things at the same time, and that's what makes it faster, right?
That makes sense. So that's the reason, right? So imagine, even if it's like you said, 1, 0, if you split it, it exponentially 2 powers, and it can get really big, versus quantum that there's no that exponential increase.
So what's 2 to the 5 for a classical computer is 5 for a quantum computer.
Exactly.
Wow.
What this means is that what's the core of it? It's the core of quantum computing is about qubit being 0 and 1 at the same time, versus that's not the case for the regular computers.
Yes, exactly. That and entanglement and other things.
And
But
entanglement.
the basis is that if you operate on a qubit, you're doing more than one thing, but it costs one thing.
That is so fascinating.
Yeah.
I can
It's pretty
imagine
fast.
so many unlocks, right? With that.
Yeah,
Oh
that's
yeah, so
crazy.
many. Yeah, for example,
My
like
God.
factoring big numbers, right? Like factoring a big. If I say, for example, 15, you say 3 times 5, right? That's factoring a small number. But if I give you a number of 1,000,000 digits that is hard to factor, it could take the computer millions of years, a classical computer, to factor it, right? And that's why RSA cryptography is good, because it's not like it's bulletproof. It's just that the computer's going to take millions of years to solve it. With a quantum computer, you can factor numbers pretty quickly, and so that would break that type of cryptography, right?
Wow.
And
Interesting.
yeah, there's a lot of things you can. But here's something interesting, right? Like people think it's going to be all quantum. No, it's going to be one tiny piece of quantum, right? Like the computer's going to be mostly classical, and then one tiny piece is going to be
I
quantum.
was thinking the
Yeah.
same thing.
Yeah.
I was thinking about the interaction, right?
Yeah. The classical's not going to stop, because there's many things that a classical computer does well, right? Like adding numbers. That's classical. That's quick,
Yeah.
right? If I make a quantum computer, add numbers, it may say, well, 2 plus 2 is 4, but with a small probability is 500. I don't want that, right? And so, because everything is probabilistic in a quantum computer, right? So I see it as an airplane, right? Like an airplane is most of the time a bus, right? Like when it's parked, it's a bus. When it's driving, picks up the passengers, it's a bus. And it only becomes airplane, like gets the wings out when it needs to, right? Like when it goes, okay, now I need to go from New York to Paris. So then it uses the wings. But other than that, it's a bus, right? And so a classical computer is like that. Like it's a classical computer when it picks up the data, when it operates with the numbers, and then there's one step in the algorithm, one step that would take 1,000,000 years. Then it gets the wings out, and then it uses a quantum thing, and then it reads the answer, and then it continues being classical to process the solution, right? So like it's still gonna be mostly classical and a little quantum bit. Quantum bit's the wrong word, but a little quantum part.
Wow,
Yeah.
that's so cool. I mean, it's really analogous to, for example, like a lot of stuff, right? Like CPU versus GPUs. That's the thing
Yeah.
that came
Pretty
up.
much.
Like,
Pretty much, yeah.
and like even your ML models versus like Gen AI
Yep.
models.
Exactly.
You're not
Yeah.
going to use Gen AI to do like classical predictions of stuff or classifications.
Exactly. Yeah, you're not gonna make it generate an image of the answer. If you need to add 1 plus 1, you just use a classical thing, right? Like, so you never use. Yeah, you used what's big. Actually, you mentioned Gen AI, and actually, we believe strongly that quantum computers are better at generative AI than classical ones, and then the classical ones, I believe, are better at supervised.
Mm.
Because it's a deterministic machine, right? Like a quantum computer, a classical computer is a deterministic machine. If you give it the input, it gives you the output for sure. That's perfect. That's great for supervised learning, because you need to give it the input and get out of 1 or of 0. You try that on a quantum one, and it's hard. There's great work, by the way. There's great work by Amira Abbas and Maria Schul and some people. You should have them in the podcast, by the way. By some people that have done like supervised quantum computing. But then there's the opposite happens with generative AI. Like classical computers are bad at generative AI, even though they're great, but because we have big computers. But in reality, a classical computer is more of like a deterministic machine, right? Like whatever you give them, they read off a script. They can't come up with a random number. It's a pseudo-random number, right? They can't come up with a random number. They have to pretend it's random. Generating stuff is bringing out random numbers in a way that they follow some distribution that looks like an image or looks like text, but it's really random numbers. Quantum computer is a random number generator whether you want it or not. And so like we did some experiments on quantum generators of the same size, a little algorithm with a few qubits and a few bits, and we noticed that the generating power of a quantum computer was, it just picks up more. It just would pick up your data and generate stuff that looks like the data but is much different. On the other hand, a classical generator would just sort of pick your points and find points that are really close to those, right? So I do believe that quantum computers, I may be wrong, but I do believe that quantum computers are better at Gen AI. And I can also get philosophical about quantum computers if you want, but I don't know if you want to open that door.
Go for it. Go for it.
That was my next direction, Luis.
Perfect.
Like really, like quantum computing to me sounds like so human, like to some extent, and consciousness, and this whole thing about humans. Like I definitely see quantum computing, yeah. So please go ahead.
Well, I have a lot of conversations with friends. By the way, I just thought of like 10 people you should have in this podcast. There's with my friend Alejandro Perdomo and my friend Caitlin Gilly. We have and on others. We have great conversations because you can't get quantum without getting philosophical, right? And
Yes,
so here's the
absolutely.
thing. Let's tie it back with the things that a human cannot do. I can tell you with a lot of certainty, and I may be wrong about everything I say, but I can tell you with a lot of certainty that a classical computer cannot exhibit any kind of empathy or any kind of intuition because it's just maximizing some variable. Any algorithm maximizes some variable, and some things are just not measurable, right? Then here's the thing. I don't know if I can say the same thing about a quantum computer. I don't think it does, but I can't assure you that a quantum computer will not exhibit empathy or will not exhibit some kind of intuition, because there's a little part of the quantum algorithm, a tiny part, where you're measuring the qubit and you're pretty much flipping a coin. And this process is entirely random. It's not pretend random like the classical computers. It's fully random. So random that if I were to replicate the conditions of the universe and flip the same coin, I may get something different. Belief, right? Like can't try that experiment with belief. And this random thing, I can't tell you that it's not entangled with human consciousness or with God, whatever, you know what I mean? Like if it's a completely random process that doesn't depend on the inputs, I mean, it depends in the sense of probability distribution, but it's not deterministic. There's nothing of me that says that thing didn't entangle with my consciousness, right? And then came up with a that those human conditions didn't get into the algorithm just because it's a part that nobody controls, right? Like the quantum part of the measuring part of a quantum algorithm is something that nobody knows how it happens. So
Maybe
I think it may be that are the higher skills that I told you were not replicatable by a computer. They may be replicatable by a quantum computer.
Luis, maybe we are all quantum computers.
maybe, yeah.
Wow. That's crazy. That's so cool though. My God.
Like imagine the aliens that we are all looking for existing on Mars and others. Maybe we'll create a bunch of
Yeah.
quantum computers and throw them on Mars, throw them
Yeah.
on others, and they create cities. And
They will, yeah, maybe they'll
that will
Wow.
be
Man,
amazing.
they'll
so
entangle
fascinating.
with some other consciousness or something.
Yeah.
So fascinating. So fascinating. I think, man, that was such a fun conversation, Luis. I think, man, like it gets me thinking quite a lot. Honestly, I've watched some quantum computing, like when Microsoft had their chips announced,
Yeah.
Yeah.
that was a big
Yeah.
deal. And then I was trying to look for what does this mean, like stuff like that. Like not much out there in terms of the implications, like what it's doing, that kind of stuff. And so I'm glad we get a front row seat to all the stuff that you've looked into.
Yeah. Also,
Thank
not
you.
much detail about the simplicity of quantum computing. People get into the depths of it. So I
Yeah.
hope people understood like the basic details, like qubit and
Yeah.
entanglement, like the basics of it to some
Yeah,
extent.
and
Yeah.
remember, if to anybody listening is, if you're confused about quantum computing, you're basically at the level of the experts because they're confused about it so much.
Yeah, I love that punchline. Okay, so I think we're getting to the end of the episode here. So we like to ask every guest the same question before we end. What is one most underrated skill that you think a data professional should have?
Ooh, that's a good question. Yeah, I feel like I'll tell you one that's I think overrated. Knowledge I think is overrated. Not that knowledge is not important, but I think we put more emphasis on that mainly because it was so useful in the past when you would learn something and use it for 50 years. Right now things changed a lot, and I feel like you have to learn new stuff. So I would put a lot more emphasis on malleability, right? Like the capacity to change topics, to change gears and to learn new things. Like when I hire someone, I actually look more at like how many new things they've learned, how many times they've embarked into a new project, because things will change pretty soon, right? Like in 5 years, we don't know what we'll be doing because it'll change completely, and we need people who are ready for that. So I think of malleability a lot more. I like to think of an analogy of like physical fitness, right? Like if I'm gonna hire someone for, I don't know, a sport, like maybe running and swimming, like running an Ironman or something. If I have somebody who run marathons, I know that they will do well, even if they don't know how to swim, right? Because I know that they have the fitness and the determination and all that stuff. Whereas if it's someone who knows how to run and how to swim but doesn't do it very much, it may not be that likely. So I actually, yeah, I definitely think if people have changed topics a few times, learned a few different things, and are able to learn what the new technology is, I think that that's a skill that that's the next sort of big skill that we're gonna need.
Thank you so much, Luis. Where can our audience find out more about you?
Serrano Academy. So my page is serrano.academy, but the best place is my YouTube channel. My YouTube channel is called Serrano Academy, and that's basically all the stuff that's in my brain is in the YouTube channel, because every time I think of anything, I just put it there. So if you see it, you know as much as I do. And yeah, that's where I put all my stuff. LinkedIn also, Luis Serrano. I have a lot of contacts there. But the YouTube channels is the place.
Nice, awesome. Well, it's been a really wonderful episode. Thank you for coming on. Travia, do you want to close it out?
Yeah. Luis, thank you so much. I think this has been a one-of-a-kind podcast. We didn't do the basics of like human intelligence and understanding how we all know way more than what we think we know. I think that is like a key concept that we tried to look into today. And thank you for coming in and helping us understand that about ourselves.
Thank you so much for the invitation. It was an honor. I'm a big fan of your podcast, so thank you, and great questions. We had a great conversation, so I really enjoyed it. Thanks.
So awesome. Thank you. And to our viewers and listeners, if you enjoyed this episode, please like and subscribe. And if you have questions for Luis or any of us, please drop them in the comment section. We try to respond to every single one of them. Otherwise, we will bring you more content just like this in the future. Thank you, everybody.
Thank you, guys.
Thank you.